Howdy, youngsters. We are looking at sections 4.4, 4.5, 4.6, and 4.7. You might think that is a lot, but we're taking just a little bit from each of those, and we're looking at them because in this section, we're only looking at 12 problems, even though we're dealing with 4 different sections. And for the newcomers, where to find all this stuff is you're just going to go into Blackboard, and you'll find all of this under your learning activities. And then there'll be a chapter 4 for you there. And then we are looking at 4.4, 4.5, and 4.6, and 4.7. And so in each of these, you'll find the PowerPoints that we're going to be looking at, as well as a handy-dandy little video. This video that I'm making is looking specifically at the problems from the Math Excel assignment. So this number 1 will be very similar to your number 1. So in 4.4, we are looking at CPCTC. So this is congruent parts of congruent triangles are congruent. And so the big thing is here, we have to prove that the triangle is congruent before we can use this. And so here's an example where we have this figure, we have given information. Once we have proven by any of these theorems, we have angle, angle, side, 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 angle, side, angle. Once we've done that, then we can pick corresponding parts of these congruent triangles, and we can then prove that they are indeed congruent. So if we look at this first problem here, this is what we're given, and sometimes it's a good idea if you break apart these triangles and look at them separately. And then this is in number 3. Since it's basically the same side on top of itself, that's where we get reflexive property. And sometimes it's very helpful just to label. What is this? Is this a side or an angle? It's a side. Is this a side or angle? It's a side. Is this a side or angle? It's a side. So it's very easy to see, we can prove these triangles congruent through side, side, side. Once we've done that, now we can say that any of the corresponding angles, and in this case, it's angle M is congruent to angle R by CPCTC, or we can just talk it out. So that's coming from section 4.4. Here, looking at this section, we're looking at isosceles triangles. And when we have isosceles triangles, here are the parts of these things. All right, and so we have the vertex angle, and then we have legs and the base. And so we need to know what we're talking about and how to label these things. And so base angles, these are angles that are opposite of the legs, and the base is opposite of the vertex angle. So when we have legs that are congruent, then that must mean that the base angles are congruent, and vice versa. If the base angles are congruent, then we know that the legs are also congruent. So in this particular problem, since we know that these sides are congruent, then I know that these base angles have to be, so that's where the other x comes from. Then I know that the interior angles add up to 180, so I can just have x plus 78 equals 180, and solve to get 51, and we're done. Now in this next one, we're looking to find the values of x and y. We're still looking at what's going on with these isosceles triangles. And so here we're dropping a vertical here, we're cutting that in half. And we know that because the two in that vertex angle, we see these small little arcs here that let us know that they're congruent. And that lets us know that this vertical angle at D creates a right angle. That's where this 90 comes from. So if we look at the larger angle or triangle gets cut into 2 smaller triangles by BD, I could then say, okay, 49 plus 90 plus I don't know is equal to 180. So that's where this comes in, and that's where we get 41 for our x, because we know that they're basically mirror images of the same thing. And then for our y, we don't have to do any calculations. Since these the vertex angle has been divided into 2 equal parts, that means that its opposite sides must also be congruent. So we just, whatever this number is here, must also be for y. Here we're looking at an equilateral triangle, and all that means is that we have all equal sides, and I broke them apart here, so we can look at them separately. So I have ABD, this one here, and BDC, this one over here. And so when we break it apart, we're really concerned about what's happening at this entire angle ABC. And so at one part of it, I have 60 because all of these angles in an equilateral triangle are 60. And then here we have a similar problem like before. We have an isosceles triangle. So I know that one of the base angles is 67, therefore the other must be 67. And looking for the vertex angle, I add those together and let it equal to 180, and I find out that this is 46. A lot of times people get this wrong because they just put 46 in there, but it's asking for the entire angle of ABC, which means we have to add this part of 60 and the part we found of 46, and that gives us 106. Once again, looking at an isosceles triangle, we are given that the vertex angle is 84. It's very helpful to draw this out. It's not necessary, but it's helpful. And we know that our base angles have to be equal, and that's how I get this equation. And so I have x is equal plus 84 is equal to 180. I solve and I get 48 for each of those. And then the next problem, kind of have a couple of triangles put together here. And so this first part, we have to look at this linear pair. So everything back in the chapter 1. And so I know that 128 plus something must equal 180. So that's where this comes from. And once I get 52. Now I can look at this smaller triangle here on the left. I know I have 90 degrees from the right angle. I know I have 52 from what I've just found. And I don't know from m. And so that's where I get this equation. I solve for m and I get 38. And then if we look at this last triangle, I see it's an isosceles triangle, which lets me know that 128 is the vertex angle, and lets me know that both of these base angles have to be equal. And since they call it n, both of these are n. So I set up that equation, solve, and I get 26 for n. Here, pretty simple things happen here. This is letting us know when we're getting into the hypotenuse or the leg theorem. And this is another way to prove a triangle is congruent. And this is a special case because we have to have a right triangle because we're dealing with legs. And so basic little how to label these things is the sides that create the right angle, these are called legs, and the side opposite of the right angle is called your hypotenuse. And then we have, if we know that we have a leg congruent to the other leg and the hypotenuse congruent to the other hypotenuse, then we can use that just like we use side, 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 just like we use angle, angle, side, or angle, side, angle. We can use H-L theorem to prove that a triangle is congruent. So that's kind of what's happening here. And we just need to make sure we get them in the right order. So I have them highlighted here for corresponding angles. So G is congruent to K, H is congruent to L, and M is congruent to J. So I have those highlighted here. It's easy to see because all the other ones are yes as well by the same exact theorem. We have to make sure we get the correct order. Here we're looking at a proof. A lot of it, as you can see, highlighted in yellow is being given to you. Here, since we're given perpendicular lines, then we simply know they're right angles because of the definition of perpendicular lines. Another one of them is the definition of right angle, but we're not told that it's a right angle. We're told that they're perpendicular, so that's the only reason we can use. And then we said they're right angles, and this is by definition of a right triangle, which simply states that you have an angle that's a right angle. We have something that's given, and here's the first time, or I'm sorry, and then we move over here is another given, m is the midpoint, and if that is the midpoint, then that says that the distance from t to m is equal to j to m, as you can see here. And then this is the first time that we're using the H-L theorem or the hypotenuse leg theorem. And this can only happen when we have a right triangle. Here we use the hypotenuse leg theorem again to help us solve for x and y. So we're setting corresponding sides equal to each other. So that lets us say that x is equal to y plus 6 and 3y is equal to x plus 2. As you can see with these separate equations, there's nothing we can do. So we need to substitute. So I know that x is equal to y plus 6. That means this x is y plus 6. That allows us to have one variable in our equation. It allows us to solve for y and get 4. Once we know y is 4, then we can substitute that back in here. I know y is 4. And then that lets me know that x is 10. Here we have, we're going to have overlapping parts here in 4.7. It's kind of what's happening here. And we've seen parts of these things happening before with the reflexive property. And that's the same thing that's happening here. So we're kind of taking triangles and we're putting them on top of each other. And if we do that, then that means that those parts are congruent to each other. Another way to kind of look at this is if you see the letters, right? Both of these have D and E. Therefore, the side DE is the common part. And here, they only have one letter that's common, F. That lets us know, 1, it's F. 2, that it's an angle. So if it has 2, then we know it's a side. If it has 1, then we know it is indeed an angle. And then we have a proof using this. Highlighted are givens. Once again, that reflexive property again, it's on top of itself. I'd labeled these. This is an angle. this is an angle, this is a side, therefore this is angle, angle, side. Please keep in mind, it just is a coinky-dink that it happens to be in that same order. We do need to still go over there and make sure that it's not angle, side, angle. And then once again, this is kind of putting everything together. We've proven that the triangles are congruent, and therefore we can say that these part is congruent by the corresponding parts of congruent triangles theorem.